today. Margarita got her PhD in physics last year from MIT under the supervision of Professor Liang Hu. And then she started working as a postdoc at Caltech. So Margarita has done a lot of interesting work on both quantum matter and quantum information. In the direction of quantum matter, she did a lot of interesting work on superconducting diode effects. And today she's telling us about her more recent work on quantum information. So I think Margarita's work is really a very special combination of some phenomenological work and some more conceptual work. And the more conceptual work may ultimately lead to some practically useful technologies. That's great. Thank you.
Thank you very much. Thank you. Yeah, thank you for having me here. And yeah, I wanted to encourage you to ask questions because my slides are designed to mostly give motivation and the background on the topic. So it would be great if, yeah, the questions arrived while given the talk. And then I will just give a big picture of what we're doing with this work. So yeah, I would like to start by thanking my collaborators. It is Shankar, who's a graduate student, a senior graduate student at MIT, and Ethan, who is a Miller postdoc at Berkeley. And I would also like to acknowledge very useful discussions with Peter Gács at the Boston University. All right, so yeah, so now I'm going to move on to motivation, and it's going to take a big chunk of time. So if we are interested in storing quantum information robustly, there are several different, completely different ways to do this. One of them is to have a Hamiltonian system such that we don't take out any energy, so it's energy conserving system, and then it becomes it interacts with the environment, so now it becomes open, and environment is large and it's at some given temperature, and we allow it to thermalize. So if such system takes incredibly long time to thermalize, specifically we are interested in a situation where this time goes to infinity in the thermodynamic limit, we would say that such a system exhibits self-correction. Then another example is what we call fault tolerance, is when we are allowed to actively pump out energy from the system, and that's the what we have on the right-hand side, and that's what I'm going to talk about today. But I'm going to try to motivate why it is still very fundamental question and also practically relevant one. So I'd like to first compare what's going on in classical versus quantum systems. So if we wanted to store classical state reliably, meaning classical bits, then we know that we cannot do it passively in one dimension because there exists no spontaneous symmetry breaking that we can use to store to have two degenerate states that for storing information. Okay, and then usually when people talk about this topic, they say that Ising model is a good quantum memory in 2D. However, if we are using the stringent standards of quantum information, a model that is not perturbatively stable cannot be a good passive memory. And the problem with Ising model is that it is not robust against longitudinal field. It would actually lose its memory in a constant amount of time, in a very quick time. So because this model is not perturbatively stable, it's not a good classical memory either. And the only candidate that is known to me to be a good classical memory is actually gauge theory. And so intuitively, you can understand why that could be a good memory. It's because gauge theory has a chance of being perturbatively stable. And this paper that I'm citing on the slide shows some arguments in favor of that being the case, and as well as some numerics, but no rigorous proof. So actually, even classical memory that is truly robust is only known so far in 3 dimensions. And in 2 dimensions, there is not a known candidate. Then what do we have on an active side? So on active side, we still want a completely scalable solution, meaning that only operations that are allowed must be local. However, we are allowed to pump out energy from the system, so we can have small coolers, small local coolers, basically. So an example of a system operating in such a way would be a Thom's rule. So this is a rule that basically takes domains of the 2D Ising model, and it's a small cellular automaton that basically says that that is trying to shrink those domains in time. So below we see a simulation of such a rule. And that actually is completely stable. It is perturbatively stable to an arbitrary perturbation, and the memory survives for a time that scales exponentially with the system size. And then surprisingly, despite it not being possible to store, to have classical memory in one dimension in equilibrium, we actually can have classical memory in one dimension if it is active. And that's a really surprising result. There existed a conjecture in classical computer science and dynamical systems around 70s that stated that it is impossible to stabilize a one-dimensional classical memory using completely local rules. However, in this paper, actually in the preceding paper, so Peter Gács has two papers on this. So in one of his papers in 1983, I believe, he disproved this conjecture by showing that there exists a completely local system that stabilizes one-dimensional classical memory. And the system works hierarchically, and it hierarchically simulates the same action at every single level. And so basically this action scales, the size of this action scales with each level of simulation, but also reliability improves. And this is sort of an example of hierarchical self-simulating machine. And I'm showing here just a small simulation of a different cellular automaton, which is game of life, which is also known to be self-organizing. Here's an example of some self-organizing behavior just to illustrate this. And there's also a much simpler construction that is called Tsirelson's automaton that stabilizes a one-dimensional Ising model state for an exponential amount of time. But there is a caveat that I'm going to explain in a moment that makes it not a very good classical solution. Nevertheless, that's the one-dimensional automaton that we generalized to make it work for two-dimensional toric code. Please let me know if you have any questions at this point. All right. So on the quantum side of things, when it comes to passive Hamiltonian memories, it is known that four-dimensional toric code that has a loop-only excitations is a good memory because there exists a surface tension of membranes that prevents them from proliferating even at finite temperature. So there exists a finite temperature topological order that can be used to store a qubit of information for a really long time. In 3 dimensions, this is a big open problem currently. No one knows whether it's possible or not. And the lore says that it is impossible to store quantum information in 2 dimensions under certain assumptions, and has been rigorously shown under very specific assumptions so far. But it's widely believed that it's impossible to store passively store a qubit of information in 2 dimensions. And that is an analogy to impossibility of passively storing 1 bit of information in classical systems. So now when it comes to active memory, again, we have completely local physical operations that are now allowed to pump out entropy of the system and dump it into environment. In 4 dimensions, similarly to the situation between Ising with Thom's rule and Ising model, we have now this phenomena of dimension doubling between when we go from classical to quantum. So 4D toric automaton can actually be actively corrected by a pair of 2 dimension of classical Thom's rules that actually operate in 4D. One Thom's rule operates on X-type excitations and the other one on Z-type excitations. And the difference is that, so this is very similar to how in 2D we can correct classical Ising model with Thom's rule. So each sector of the 4-dimensional toric code is somewhat like a single 2-dimensional classical Ising model. The only difference is that on the passive side, 4-dimensional toric code is a good passive memory, and that's because it's a gauge theory, unlike the 2D Ising model, which is not. So, and here we basically see heuristically an example when something in n dimensions in classical world gives rise to an analogous phenomenon in twice as many dimensions in quantum world. So by analogy, one would think that if we have an active classical rule in one dimension, that there could be an active quantum rule in 2 dimensions. And basically, beyond 4 dimensions, there is no stable known active memory. There was no stable known active memory until now. And this is the question that we addressed in our work. And basically, we took inspiration from these one-dimensional constructions, but more specifically, we generalized this simpler construction such that it works for 2-dimensional toric code. And I would like to also remark that while it seems like the approach on the left-hand side seems to be a little bit more physical, a more realistic, in some sense, approach is the one on the right-hand side. And that's because we are unlikely to have a model that truly realizes a thermally stable topological order in real world in any material. So most likely, if we have such a system, if we end up having such a system, it will be an engineered system. But if it is an engineered system, it is basically local engineered interactions that are active in a sense. But if we are already using active interactions, active way to simulate quantum matter, then there is basically no difference between deciding to simulate something that behaves in an active way or in a passive way. It's as hard to do both, either of them. And it looks like active pathway gives rise to more results. So in reality, any system that is of practical relevance as of now seems to be active in any case. So why don't we study active systems more? So, and to address a common misconception, let me also say what's known currently in the literature on 2-dimensional and 3-dimensional memories, because people frequently attempt to realize 2-dimensional topological order in quantum simulators or quantum computing platforms. So why is that not a good passive or active memory? And the reason is because when people realize, say, 2-dimensional toric code in experiments, it requires measurement of stabilizers that detect excitations. And the measurement outcomes of those stabilizers have to be stored for an extensive amount of time for the entire space. And in total, it roughly scales as L cubed per system sized L by L. Then after a certain amount of time, we would run a classical algorithm that has to be non-local. So it's a global algorithm. So this algorithm would have to take the entire input, and it will run in polynomial time, meaning that its runtime must scale with the system size. And in true limit L goes to infinity, this algorithm will start experiencing lag. And then finally, we would have to feed back a result or condition or whatever we prefer to do. So basically, systems that behave in this way are usually called quantumly local, meaning that having only local quantum operations, such as measurements and unitary, suffices to realize them. But it's completely classical and non-local, meaning it requires a global decoder, such that if you imagine a realistic classical hardware, its runtime should scale with the system size. And basically, if you truly take a thermodynamic limit, L goes to infinity, this system must not be scalable. And to highlight how much non-scalable it is, I would like to bring up this recent experiment by Google's team, where they demonstrate 3x3, 5x5, and 7x7 surface code. And in their press release, they already mentioned, and in many of the papers as well, that the global decoders already pose a delay problem for the currently existing ways to realize toric code. So it is a practically relevant problem to try to remove that issue, the global decoding. And if we had so all of this active error correction by design is local. So if we had a local decoder, that by definition would not require storage of measurements and global processing. So that would at least be a candidate for solving this issue. And maybe to motivate this study a little bit from more fundamental perspective, I'm citing here one of the first papers, basically actually the first paper that proposes to consider two-dimensional toric code as a quantum memory. So it is a paper by Dennis Landau, Ptaff, and Kraskell. So they mentioned that there exist 3 ways to achieve a robust quantum memory. One of them is to introduce a hierarchical organization that is alike to Peter Gács's construction that I'm talking about today, in a sense. The other method is to introduce more spatial dimensions, and that is the 4-dimensional toric code that actually was also introduced in this paper. And finally, the third strategy is introduce a modest amount of non-locality, and that is the 2-dimensional toric code with the global decoding that was also solved in this paper. So basically, the second and third methods have been known for 24 years at this point. And the first method, that is a local method that would generalize one-dimensional memories to a quantum setting, has not been known ever since. And there have been numerous attempts, and none of them succeeded. And
question?
Yep,
Can I ask a question?
Yep.
In the previous few slides, if we go back 2 slides,
Here.
One more. Maybe still one more. Yeah, this one here. It says this is the only way. Is this a folklore, or is it some rigorously proved formal statement?
So the second, the fact that you need a non-local decoding, or
yeah.
So these are the only known. So the point is that the only known decoders for the 2-dimensional toric code and 3-dimensional toric codes are non-local, and there does not exist a local solution. And in our work, we propose the first local solution that works on stacks of 2-dimensional toric code in 3 dimensions.
Yeah, but I was asking whether it's a belief or it can be proved that such local. Oh, okay.
So it was believed that it's possible, but no one knew how to do it.
Okay. Thanks.
Yeah. Thank you. Let me know if you have any more questions, please. So what kinds of constructions are we trying to generalize to the quantum setting? So the most famous one is the Gács automaton. This is the one that really solves the problem of local classical computation in 1 dimension. And the first solution is 1986. Sorry, I think I misspoke earlier, the date earlier. And there is a revised version of the paper that actually has been updated last year. And this is a very remarkable automaton of a very high complexity. In fact, the referee of this paper wrote a reader's guide that is 50 pages long, and it's also not the lightest read. And the point is that it has many very remarkable properties. It can store and concentrate classical memory. It can perform universal classical computation, and it exhibits self-organization, and it is translational invariant. So it's a very remarkable construction. The drawback is that it's extremely complicated. However, there exists a slightly simpler automaton that is called Tsirelson automaton, and that's a paper that is only cited order of 10 times over the history. And that automaton is somewhat similar in that it is also a hierarchical construction that is self-simulating at different levels, different scales, and it preserves a 1 bit of classical information encoded in the state of a 1-dimensionalizing model for a time that scales exponentially in the system size. The issue is that it does not really disprove the positive rates conjecture in classical statistical mechanics, because it is not truly a local solution in a very subtle sense that I will explain in a bit. So in our paper, we take Tsirelson's automaton and we turn it into a truly local solution for the 2D toric code. So the way our solution works, it performs local measurements and local feedback, and we never store measurement outcomes. It is also a hierarchical construction. And the lifetime of our memory will scale exponentially in the system size with some additional factor of beta that is larger than 0. And technically, because such a system will be perturbatively stable and robust to an arbitrary local weak noise, this is a robust phase of matter. And to the best of my knowledge, it's the first example of such a phase below 4 dimensions. That is truly robust and has generic ground states. One caveat is that just because of that small issue with Tsirelson's automaton, the 2-dimensional solution breaks translation invariance in both space and time, making it not, so breaking this time translational invariance makes it not truly classically local. However, we can trade one temporal dimension for an extra spatial dimension. So we'll have a solution in 3 dimensions that can take care of L stacks of 2-dimensional toric codes. And this solution will be translational invariant in time. And that makes it fully local. So our solution is technically a solution in 3 dimensions for stacks of 2-dimensional toric code that is fully local both classically and quantumly. And the best known results before was the 4-dimensional toric code. So this is the first example that works in physical dimensions. And this was a hard problem that was really hard to solve. And so just to mention what previous attempts have tried, there exists like an oldish work by Harrington where he tried to also sort of generalize Gács-like hierarchical construction to decode the toric code in an RG-like way. However, the way he set it up was that there exists like a blocks of like toric code that he called colonies that are supposed to reliably determine whether there is a total lot parity of anyons, and then they're supposed to decide on very large scale whether the anyons need to be paired at large scale or not. So such a solution would require you to have a reliable classical memory that stores the measurement outcomes for a long time and that makes decisions for a long time. It is a log depth memory, so this is still an improvement over existing other ways of decoding toric code, but it's not very efficient. It's not rigorously proved that it works, and it's not truly local. So and it's not truly fault tolerant if you assume that anything can fail, which is the usual assumption of premise of fault tolerance. And this concludes my introduction. So please feel free to ask me any questions.
I have a question.
Yeah.
What does a non-equilibrium quantum stable phase mean? Stable quantum phase?
Well, there does not exist a rigorous definition of what it is. So really, it's up to it's in the eye of beholder. So basically, it could be so for example, we could call a stable state of an open quantum system such a non-equilibrium phase, or some people would call like steady states of driven systems also non-equilibrium quantum phases. Yeah, but like I don't think that there exists an agreement on the proper definition of non-equilibrium phases.
But what's your definition in this talk?
So in this talk, we don't really address this question. I'm just bringing, I'm basically saying that loosely by some loosely speaking definitions of what non-equilibrium quantum phase is, these properties that we already have here meet those definitions, meet that definition.
Okay, thanks.
So it's perturbatively stable, and it is, slow dynamics for an exponential amount of time in the presence of noise or interactions with the environment. So if there are no more questions, I will explain how Tsirelson automaton works, because we really then try to extend it as straightforwardly as possible to operate on 2-dimensional toric code. And the reason it is relevant is because there indeed exists a relation between 1-dimensional Ising model and 2-dimensional toric code in the sense of excitations, right? So if we think about 1-dimensional Ising model through the lens of stabilizer codes, then we can only detect the presence of not flipped noisy domains like this, but only the presence of domain walls between different domains with different orientation. So then resisting noise from environment in such a model would mean that we are detecting pairs of such domain walls, and then we pair them up to clean up the domain. We decide how to pair them up, and then we flip everything between this pair of domain walls to clean up the domain. So this is a problem of pairing point-like excitations. And it's a hard problem if you want to do it truly locally. Then and robustly in the presence of noise that keeps happening as you keep correcting, because there's like a light-cone restriction on how fast things can move and things can pass information around. Then in two-dimensional toric code, we also have point-like excitations. These excitations sit either at the vertices of the toric code or the plaquettes, and we are also pair them up arbitrarily. And if the noise is, and if we do this using like most likely or the minimum in a minimum weight way, and the noise is weak enough, that would clean up a toric code while preserving its logical state. So the problem of correcting the noise acting on the toric code is also a problem of matching point-like excitations. The only difference is maybe that now these excitations can move around in 2 dimensions, and in 1D Ising model, they were restricted to a line. So then if we learn how to correct point-like pair up point-like excitations in 1D Ising model, that gives us hope that we will be able to come up with a construction that will pair up excitations in a 2-dimensional toric code. So, so this is part 1 basically of what we need. So the way Tsirelson's automaton works is that we need to set up substitution rules. So this is the first substitution rule. Whenever we see an, so this is not the Tsirelson's automaton. This is an example of what substitution rules are. So the first substitution rule here is we replace every orange tile with a yellow tile. The second substitution rule is that we replace every yellow tile with a tile shown here. And then every next step, we just use the pair substitution rules. And you can verify that this is really what happens. And this way we can generate self-similar tiling that really, from which we really can read off what it started from. So a similar principle will be applied in Tsirelson's automaton. So first I'm going to explain the way Tsirelson talks about this automaton, and then I'm going to explain the physical meaning of, or like more like quantum information way of thinking about this automaton. So, so there are 3 operations. These operations are depicted here, and the time goes up, and dots correspond to classical bits. And so this operation, the first operation, corresponds to doing nothing. The second operation corresponds to swapping 2 classical bits. So this is a swap operation. And the third operation is a majority vote. And this is a repetitive majority vote. So we have 3 bits to begin with. Then we compute a majority on these 3 bits, and we copy the outcome on the 3 output bits in the system. And basically, such a majority vote performs, it can correct a domain of size 1, an error that occupies a domain of size 1. So this is a technical and error correction operation on a 3-bit repetition code, or on a size 3 Ising model. It's not very effective, but it's what we need to get started. So these are our elementary operations that we're going to use to compose them into a circuit in space-time. So first we write down level 1 gadgets. So these are error-resisting better versions of the gadgets that we had at base level. So X1 is the idle operation, but it is an idle operation on a 3-bit encoded code. So now it's sort of like a logical state of an Ising model, or like which is basically a symmetry sector of an Ising model that is capable of resisting a single error if you repeat this operation. For example, if we have an input that looks like this is already a corrupted input, but the majority of this input is 1. So it's basically we're sending an all 1 state, and the output will be an all 1 state. So it resists an error, and the output is still all 1 state. The next example is trying to flip a corrupted logical state that is 1 with corrupted logical state that is 0. And it will start by correcting the errors, single bit errors, and then flipping, then applying either idle or swap gates of the 0 level in a pattern such that it ends up actually swapping things. So you can actually track what happens to a bit by just following the wire here. And then finally, this is a reliable majority vote. So it computes a majority on 3, let's say 0, 1, 0, on 3 logical bits encoded in 3-bit repetition codes. So in this example, we have these 2 states are corrupted. And the first layer of error correction will correct that. So now we have 0, 1, 0. And then there will be a pattern that will actually distribute the domains in a particular way. And if everything that we input was majority 1, actually the outcome would be all 1s. And basically you can do this exercise and convince yourself that if we follow this up by another layer of error correction, this is a proper majority vote that operates on encoded input. So this is like a larger scale operations that are more reliable. And then it turns out that we are capable of creating a more and more reliable hierarchical operations like that. And the way it works is that it works by a substitution rule. If we had, like, for example, so definition of xn operation is the same operation. So we can write down operation x1 that I showed on the previous slide as a circuit comprised of level 0 operations. And then the operation at level n is basically the same circuit, but we substitute level n-1 gadgets in there. And then we can continue to substituting the circuit, and we will find that actually xn gadget is just a large circuit of a size operating on 3 to the n bit repetition code, or in other words, on a Ising model defined on a line of a size 3 to the n, that consists of, that is a circuit that is made out of only x0, y0, and z0 operations that I showed on the previous slide. And similarly, we can define hierarchical yn and zn operations. And you can also show that each of these operations is capable of correcting a corrupted block of a corresponding size. So for example, this guy would be technically resistant to flipping a domain of size 3 to the n-1. So they're hierarchically better and better resist errors. So this is a good time to ask questions because, yeah, so I kind of showed something conceptual and non-trivial right now. All right, then I'll move on. And okay, so an example of how.
Can you explain again what's the function of Z1? I still don't know what's the what's the input and what's the output. So what does Z1 do?
Z1 here.
Yeah.
Yeah. So yeah. So here we have an input that is majority 0 on 3 bits, majority 1 on the next 3-bit code, and majority 0 on the third 3-bit code. Then we run. So the time goes. Sorry. The time goes up. And then we just run the circuit. So this is a circuit compiled from Z1 is a circuit compiled from Z0s, X1s, and Y1s. And basically it consists of a layer of error correction. This is the first layer that does this. And then of a layer of sort of complicated swaps and idle gates. And this layer basically yeah, so there it's not supposed to be obvious that this performs majority vote, and I'm going to, in a few slides, I'm going to explain how to see this. But as of now, like this current circuit, you can only understand that it does hierarchical majority vote by direct verification. So if you add one more layer of error correction, and you will start with encoded inputs, you can verify that the outcome will produce the logical state that is would be the outcome of a majority vote on 3 logical bits. Does this help?
Okay, yeah, thank you.
Yeah, so I will explain why exactly it's supposed to look like this in a few slides, when I will explain how to actually think about this in a better way as well. But just to show his original construction, so if you will ever open Tsirelson's paper, this is what it really looks like. And this is, for example, a Z2 operation that is actually, right, it's a operation that is Z1 as a function of X1, Y1, and Z1, and then X1, Y1, and Z1 are also circuits of level 0 gadgets. And this is what it looks like. And for example, the gray bits are the corrupted bits. And we basically feed in an input state that is majority white with a large corrupted domain and a few small corrupted domains. And then what it does, it basically, first it splits into 3 smaller domains like this, this, and this. And then it iteratively performs the same behavior at all scales. And then it performs the same behavior in smaller scale. And finally, it corrects those domains in the smallest scale. So it sort of it performs the same operation at different scales. And the operation takes time that is proportionate to its scale. So that's in which sense this is a self-similar behavior. So I just wanted to show a picture. But now I'm going to explain a better way to think about these operations, and hopefully now it will become clear why they work. So a better and more modern way to think about this operation would be to think about them in language of fault-tolerant circuit concatenation. So if we say that our code C is a 3-bit repetition code, then I can write down any classical operation that resists error, that is capable of resisting a single error, a correctable error on a code block. And now code blocks are 3-bit blocks. If I just perform this transversally. So what is a transversal operation? Transversal operation is one that applies the same action on same qubits in different code blocks. So let me show this in an example. So this operation would be a transversal idle. So I start with 3 block encoded states, and I just apply, this is a single code block, and I just apply the same idle operation to each qubit in a code block. And I end up with an idle, obviously. But here we apply idle multiple times because we are just trying to equalize the depth of the circuit between X1 gadget and a Y1 gadget, because we just want to be able to perform them simultaneously. Now, Y1 gadget is slightly less, Y1 swap gate is less obvious. So what Y1 does, it basically, so we want to input 2 code blocks of 3 bits, this one and this one. Then we want actually to just transversally swap first one. So we're doing swap. So I want to do swap transversally. I want to swap first bit with first bit, second bit with second bit, and third bit with third bit. That's what a transversal swap is. And since I want to do this in 1 dimension strictly, I'm also allowed, before I actually swap first bit with first bit, second with second, and third with third, I'm also allowed to have some circuits that shuffles qubits of 2 blocks such that the necessary qubits become neighbors. So here we start by shuffling the qubits such that in this block in the middle, we really are swapping first bit of first block with first bit of second block, and then second with second, and third with third. And then we'll end up having, so if we started with like state 1 here and state 0 on the other block, we will end up swapping the states. So this is sort of still quite obvious, but it becomes kind of slightly less trivial when we come to majority vote. So when we try to do majority vote this way, the way it works is that we have 3 input blocks. And I want to perform majority vote on encoded input. And the way I would like to do this is that the way I would like to do this is I would first like to take these 3 blocks, and I would like to bring them closer together such that I actually can do bitwise operations. So I will just place them above each other, such that such that now the first bits of all three blocks are close by, second bits are close by, and third bits are close by. Here I'm doing this in 2 dimensions for simplicity. So I kind of move these blocks. Then I'm going to apply a majority vote bitwise. So I'm going to, this is all first bit majority vote on all 3 first bits. This one is a second majority vote, and this one is third majority vote. So then I'm applying a bitwise majority vote to 3 blocks. And then I'm going to just put the qubits where they were, back where they were. And the circuit that we see on the left actually does this in 1 dimension. So the first set sequence of swaps, what it does is it brings all the first qubits from each block into the same location, into input of the same majority vote. Then it applies majority vote to the 3 bits that are first bits, and then it brings them back. So this is a very slight modification of what Tsirelson did. Tsirelson basically he didn't have this part, but it still worked. It's still logically operated in the same way. So this is the same, basically slight modification of what Tsirelson did, except now it explicitates that we are performing a transversal gate. And this transversal gate, indeed, majority vote is transversal on 3-bit repetition codes. And that's why this gives us an encoded majority vote. So yeah, so this is a good time to ask, Johan, did it answer your question?
Yes, thank you. But I still have another question. So in your motivation, you say you can decode a toric by this local operator. And yes, I agree with that. But it seems to me the circuit depth still scale logarithm with the season size. So, but you can do it on constant time. So can you resolve my puzzle?
Yeah, we don't do it in constant depth. All our operations are local, and they don't store measurements, and they don't communicate long range, and there's nothing global about our operations. But indeed, the circuit will be, it's not even log depth, because log depth will only be capable of correcting log size errors, and that wouldn't perform as well. So our circuit, if you have L by L toric code, it will be actually L to some powers. It will be poly L depth and time. So indeed, it's a very deep circuit that would fully correct toric code. The benefit of this circuit versus usual decoding is that if the circuit actually runs live on your toric code, and the noise keeps occurring as you run the circuit, you can show that the toric code will live for some exponent to the, I don't know, to some to some quasi-exponential amount of time. It will, the logical state will survive for that amount of time. And if you run the circuit noiselessly, indeed, this circuit would take a really long time to run. Yeah, so indeed, it takes, the depth of the circuit is large.
Okay, I see. So you are doing this circuit again to
yes,
maintain information. Okay, thank you.
Yeah. Exactly. Yes, and that, so basically it's not constant depth, but it's completely but the operations themselves are completely local, and yeah, and they don't store measurements. So there's nothing global about it. So, and then you can get rid of the fact that the circuit is so deep by adding an extra dimension, and then this sort of like an extra dimension, in temporal dimension, everything is depth 1. But to really be corrected, you just keep swapping your layer, like your 2-dimensional slice of the toric code through 3rd dimension, such that once you finish swapping, you have undergone a full toric code automaton, basically, full circuit. So it's slightly more complicated. Yeah, thank you. That's a very good question. Yes, so and then we can again, so we can express Tsirelson's big circuit, the full automaton, in language of concatenating circuits. So so the way it works is that a single fault tolerant simulation of any operation will start by taking every bit, replacing it with a 3-bit repetition code, then replacing every operation acting on every bit with its encoded version that I'm showing here, which is just a transversal gate. And then we also have to perform the actual error correction regularly, but luckily we know that the error correction is just that majority gate that we had before. So, and then we basically intersperse everything by error correction gadgets. And that is the prescription of fault-tolerant concatenation of circuits by Gottesman, Kitaev, and Preskill. Sorry, by Gottesman, Eliferis, and Preskill. I'm sorry if I misspoke. And then you keep iterating this fault-tolerant simulation, and that will repeating that n times on a, for example, 1-bit input circuit, which is just like x naught. That will create a 3 to the n circuit that runs on a 3 to the n sized input. That will be a very large circuit with a very large input and a very large depth circuit. And this will be a fault-tolerant concatenated circuit that that can correct errors. And then there exists already sort of standard techniques for showing its fault tolerance, and it's quite easy. And yeah, just to show what our modification of the circuit would look like in language of fault-tolerant simulation, let me just show another example. So if we start with a majority vote and we perform fault-tolerant simulation of that, we would replace this gate. We would replace each input with a 3-bit input. We would replace the gate that acts on these inputs with a Z1, the encoded gate, which is this part. And we will, before and after that gate, we will add a layer of error correction, which is these 2 layers. And then if you want to simulate this fault tolerantly again, we basically will repeat the same thing again on each element of the circuit. So we'll take each bit of this circuit, and this second fault tolerant simulation will replace it with 3 bits. This will be replaced with this gadget where there have been layers of error, level 0 error correction here and there. Then there will be a very deep, complicated circuit that this will turn into, etc. And this one will be capable of handling much larger errors of much larger size than otherwise. Yes, so this summarizes the overview of Tsirelson's automaton in the classical language so far. So basically, this is a circuit of large depth that operates self-similarly, and concatenation of circuits is also basically self-simulation of the same operation at larger scales. And yeah, and you can show, it's not very hard to show its fault tolerance once you realize it's a circuit concatenation. So this is a good time for questions again.
I have another question. So the final goal for this circuit is to eliminate all 1 error, like the gray error corresponds to the bit 1. So you want to run this circuit to make sure the 1 disappear finally.
So what do you mean 01 error?
I'm sorry, I mean just 1. So here assume the origin is 0, and now you have some 1 error in this gray error, and you want to run this circuit to make sure this 1 disappear finally.
Yeah. Yeah, but this circuit is symmetric. It also would correct if you encode all 1 state, it will agnostically also preserve all 1 state. So
so you will keep the majority of your initial state.
Precisely, yes, right. Yeah, so it actually is a bit of information. It's agnostic to which of the states you input. It will preserve that.
Yeah, maybe I have a question. Yeah.
Yep.
I'm curious about that. Why this is called active error correction? I think this is something like a system under evolution governed by this like classical circuit. So it's more like a passive error correction.
So usually people call passive error correction. That's a good question. They call the one that undergoes unitary or Hamiltonian evolution. And in just a bit, we will see that. And actually, we don't even need to wait to see this. The majority vote actually erases the information. It's not a energy conserving dynamics. So it's not cannot be a majority vote cannot be a Hamiltonian dynamics.
Yeah. So the point is that the majority vote is not a measurement, but it is still something like modify the information.
Yeah,
it
like breaks detailed balance in a sense. Yes. So you cannot write a Hamiltonian for that.
Okay, thanks.
Yeah. So this is dissipative dynamics in that sense. Yeah. But it is completely local. And you could technically, if it was time translation invariant, which Tsirelson automaton isn't, but a Gács automaton is. then you would have been able to write time-independent Blood-Arrow dissipation technically.
Okay, thank you.
Okay, so now, so now I'd like to explain the big idea. So I don't have too much time left, and I just want to explain the big idea. So I'd like to explain the idea behind how to generalize something like this to work in 2 dimensions and on a quantum code. And that consists of several ingredients. So first of all, I usually remind people that when we are going to talk about automaton, but this is not a quantum cellular automaton, because quantum cellular automaton is a concept that is reserved for unitary, locality preserving unitary operations. And the operations that we will have are not unitary. So the first step, we are going to translate the basis operations of the Tsirelson automaton into the language of stabilizer codes. So the Ising model or a repetition code is actually a model with can be recast as a stabilizer model with the stabilizer that is just ZZ operators, which are basically the operators in the Hamiltonian. And if we measure such an operator, we will detect the presence of a domain wall at the location in the middle. And just to display things in the same fashion as for the toric code, I'm going to basically translate operations into such that they look slightly differently. So for example, this idle operation will turn into a new gadget that we will call idle operation. And then I will also, time will still go upward, but I will now show locations of qubits as edges because they will be on the edges for the toric code. So now the swap operation, we're going to turn that into also measurement and feedback operation because these are the only operations that are allowed in stabilizer codes. So for 2 input qubits, we will measure the ZZ on these 2 qubits and the potential presence of the domain wall between these 2 locations is shown by a black dot. And if the domain wall is present, we will apply feedback in the next point in time that is conditioned on the presence of the domain wall here. And this feedback is just a pair of X unitary operations on the 2 qubits. So this is local measurement and immediate local feedback conditioned on this local measurement, and we don't store any outcome. And you can convince yourself that this operation is identical to swap by just considering it the truth table of this operation. If both qubits are in the same state, like say 0, we don't need to swap them. Like swap doesn't do anything to them, similarly to 1, 1. But if we have a state that is 1, 0 or 0, 1, then there is a domain wall between these 2 qubits. And how do we swap 1, 0 and 0, 1? We can swap them by just flipping both of them. And this is basically this operation. So this operation T0 is at physical level a different operation than the actual swap, but at the truth table it is the same operation. It has the same effect, but this is now measurement and feedback operation. And then finally, we want to translate the error correction majority vote into measurement and feedback. And we will also rename this gadget. It will be called a recovery gadget now. And these gadgets will be conditioned on measurements of 2 stabilizers here and here, whose values will be stored are associated with domain walls that possibly are located here. And then it's supposed to apply feedback depending on what combination of measurement outcomes it has. And I'm going to explain how it works in just a moment, but the point is that it's also supposed to be just a very simple operation that will reproduce the truth table for the 3-bit majority vote. So what kind of operation do we want to achieve? It's conditioned on the presence of the domain walls, and there are basically these 3 non-trivial configurations that we can measure. And so on the first one, it could be either the flip in the middle, the minority domain is in the middle, and then we are supposed to and then we're supposed to correct it so the output is shown above, or the minority domain is actually outside of these point-like excitations, and then we would be supposed to just make everything continuous. And similarly in the next case, we have a a point-like excitation at the end of some flipped domain, and we're supposed to move this point-like excitation to one of those like locations at the edges of this 3-bit code. This is really the behavior that we are trying to reproduce. And what this behavior really is, it sort of it splits the one-dimensional chain that we have into what we call a one frame. So it's like a hierarchical upscaled lattice, such that inside every single block, every single cell, we either clean up a domain or we stretch a domain such that its endpoints are always at these vertices of the. It sort of course grains the input, and similarly here. So and in the end, we ended up. So this is a little bit of a complicated operation, and we ended up simplifying it in measurement and feedback language in the following way. So we will introduce a different basis, third basis of operation that we call a match gate. And this match gate simply detects the presence of a pair of domain walls nearby, specifically in the middle qubit. And then it just applies X to correct them, to correct that minority domain. So that's a very simple operation, right? And then it turns out that we can represent a proper majority vote as a 5-step sequence of M0 and T0 operations at these locations, as shown here. And that I will leave it as an exercise to a reader to verify that this is indeed a majority vote operation. So the point is that once we translate every single level 0 operation of the Tsirelson's automaton into measurement and feedback operation, the way it physically operates will change, but the circuit does not need to change at all, because the circuit is just a compilation of the gates at level 0. So from there on, nothing, like these operations are completely identical. The identity swap and error correction operations, they are completely identical in their action on classical states. And once we compile them into a circuit and we just run that circuit, they will similarly be fault tolerant in a classical sense. So now this from here, we sort of can envision how a 2-dimensional correcting automaton would work. So as we saw, the error correction gadget, it sort of coarse grains the lattice to a 3x3 lattice. And then we also know that it is a self-simulating dynamic, so it must keep coarse graining things. It's to larger and larger scales, so similarly. It just takes slower and longer time, to coarse grain things at much larger scale. So similarly, we are trying to set up a similar dynamics for the excitations in the toric code. So just to explain the big picture of this, we split the lattice into 0 cells, 1 cells. These are 3x3, and 2 cells. These are 9x9. And similarly, K cell will be a 3 to the K by 3 to the K cell. So this is hierarchical set of length scales. And we will have 1 frame, which is like level 1 coarse grained lattice for the toric code. Then we will have 2 frame, and we will have a K frame similarly. Sorry, for some reason it jumped very far. Oops, sorry. And then we'll have a K frame similarly. And then finally, what kind of dynamics we are trying to achieve that generalizes Tsirelson's automaton in an appropriate way. So basically, we'll have a 3x3 error correction gadget, and we will be able to similarly move domain walls around. And a proper coarse-graining dynamics will first always coarse-grain things at the smallest scale. And here, the smallest scale will be 3x3. So everything that's small enough on 3x3 scale needs to be cleaned up. And so all these errors fit in a 3x3 block, and they must be cleaned up. Then everything that does not fit in the 3x3 scales, and this is this error and the other error, it must be coarse-grained, meaning that it must look like a valid error on a larger lattice. So the anyons must be moved to the closest vertices of the next coarse-grained frame. And that's what we wanted to do. And then the automaton will simulate the same action at a larger scale. So at a larger scale, this error is now a small error. It must be cleaned up. And this error must be coarse-grained because it's large enough. It cannot be cleaned up by a 9x9 gadget. So basically, we'll need this to disappear, and we will need that to be coarse-grained. And finally, if the automaton keeps repeating hierarchy self-similarly, then from perspective of the largest automaton, this error will also be small enough. And the point is that the principle of work of Tsirelson's automaton shown on the left can be used to directly come up with the measurement and feedback gadgets that move things around in the toric code. So here I'm going to sort of move very fast because I'm out of time. And please ask me questions at the end if you would like to hear more details. But the idea is that we have operations that are now measuring two-dimensional stabilizers, but still move things along and match things along one-dimensional lines. That are completely analogous to the ones I showed for the Tsirelson's automaton. Then for the Tsirelson's automaton, we compile those basis operations into an error-correcting gadget. And similarly, in a toric automaton, we write down a sort of complicated rule that compiles the elementary, it's 24-step rule, that we even, in our paper, we double it for the purposes of the proof. So it's a long rule, but the point is that this rule cleans up everything that is like small enough inside this cell, this one cell. And if the error looks like this, it will actually bring the anyons to the corners of the one frame. So it has the desired action. One can verify it. So we also have an error correcting gadget to level 0. And then we also need to show, to really compile the big circuit, the self-simulating circuit, we also need to show sort of transversal gates that operate on encoded blocks. And that's what we do in our paper. We define what an encoded block is from perspective of where anyons are on this like hierarchy of scales, and then we show how to compile a circuit. And then just to show you what it really looks like. So these are simulations of its operation. So here, for example, we have two very simple errors, and the small error was corrected very fast, and the larger error took longer to correct because we required the first error was corrected by the very first error correcting gadget that takes a small depth. The second error is much larger, so it needed to be corrected by this large gadget. And these colorful block bricks that are jumping in the background are the gates that are operating on the automaton. And this is a different example that it takes even longer to correct, and we are just closing the loops here. And this is a predetermined circuit, and the predetermined circuit does simply predetermined actions. It doesn't store any measurement outcomes. So it does kind of really dumb things because of that. It's sort of like, kind of moves error, shuffles error around until it has a chance of self-similarly correcting the larger error too. So as you have seen, the small error was corrected really quickly, but the large error took a really long time. And that's because we needed to simulate the error correcting gadgets on this scale in order for it to be corrected. And then finally, if we have like a pretty large density of errors, but if it's typical distribution, that will also be corrected. It's just if the error is large scale enough, it will take quite a long time for it to get corrected. So here is another simulation. So this will take a long time to be corrected because it's a pair of errors that are far from each other. But okay, the point is that these will also be corrected. And okay, I will just mention that to prove fault tolerance, both in Tsirelson's automaton and in toric automaton, we sort of do, the method is very similar to RG in the sense that it shows that at each next scale, you're simulating the same action, but the pattern of error must be renormalized under this action. So there exists some sort of flow of error pattern that happens as time goes. So it's a dynamically generated pattern it's dynamically generated flow. And the error can dynamically keep appearing, but the flow is coarse graining. So it's like a real space RG. So that's all I wanted to say. So let me know if you have questions and we can discuss further. And then locality is the question that we also discussed. The true locality is achieved only if we consider steps of two-dimensional toric code in 3 dimensions. And then we get rid of the depth of circuit by exchanging the depth of circuit for the third direction, which is we call Z, and then just laying down the circuit in the third direction. But now each layer actually does the circuit at given depth, but it repeats it periodically. And then between these operations, we actually swap the state of the toric code further and further. And this way, toric code state will be just swapped through the entire system, while it seems like basically if we sit down in the moving tray moving frame with the toric code state, we will see that what it is experiencing is the time translational non-invariant automaton as we go through the system. But really in 3D, this is time translation invariant. So that brings me to conclusions. So I'd say that our results are sort of a proof of principle results, and we didn't spend any time optimizing them or benchmarking them seriously. And we just tried to find the simplest possible generalization of a one-dimensional rule and really try to understand the one-dimensional rule, and then to really show that it works, that it is fault tolerant. And that took this paper that just recently appeared in arXiv. We don't know how to generalize it to other codes or to other lattices, or how to optimize it. And there definitely is a lot of space for optimization. And it would be interesting to see it work with qualitatively different codes. But it seems very plausible that local decoders for other codes should exist, because in some sense, toric code is the worst case scenario. And then going further, it would be extremely interesting to find an actual generalization of the Gács automaton, which is a much more complicated construction, which actually has much more interesting properties. And one of those properties is very special, which is quantum self-organization. And the reason why it is so special, maybe it's easier to just bring up this fun fact that I recently learned, which is another example of a self-organizing cellular automaton rule is game of life. And in game of life, it's a very simple, it's also a translational invariant rule that does the same, very similar to Tsirelson's automaton, except it's translational invariant and does the same thing at every point in space. But it is universal for computation, and it is self-organizing. So people figured out a way to run game of life on game of life, or you could prepare a Turing machine on a game of life. So self-organization goes to an extent where you can do anything at all on this automaton. So this is what level of complexity can achieve. And finally, that's the direction that is very natural, but we haven't explored it, which is this clearly opens a new avenue for actually stable non-equilibrium phases of matter and physical dimensions and low dimensions that are not 4D toric code, and that have degenerate ground states, and that are robust to arbitrary perturbations. And also they seem to exhibit very exotic critical points and the transition points, which is a matter of future work. Thank you.
Okay, thank you for the very nice talk. Any other questions?
It's again a quick question. So for the toric, so far it has the base threshold roughly 1%. So in your this kind of self-correcting, like an active correction, can you estimate what's the error rate required for each qubit to make it successful?
Yes, so we didn't benchmark it very thoroughly. Tentatively, it looks like the threshold could be on the order of 10 to the minus 4, 10 to the minus 5. But again, we didn't benchmark it heavily, but in addition, we did not attempt to optimize the decoder. So this is really the most naive thing you could do. And this is already on, the threshold is probably on par with like other decoders, like Harrington decoder or cluster decoders. So it's not good, but it's not horrible, not completely horrible. And analytically, we don't have a handle on the threshold. We just know that it's positive.
Okay, thank you.
Thank you.
I have a basic question. So in terms of the concept of fault tolerance here, suppose do you mean if I implement the gates and other ingredients of the circuit with some errors, I can still do error correction?
So this would very easily work with transversal gates. So in this, the answer is it depends on the architecture. And there are several factors that have not been worked out explicitly. So if we assume this architecture, and we assume that we can have stacks of two-dimensional toric codes, then we can do all Clifford operations via finding up the gates. And these can be applied instantaneously, and these will not interfere with the operation of decoder. So in the presence of Clifford gates, it's all good. For non-Clifford gates, it's not as clear, because in any case, performing non-Clifford gate in two-dimensional toric code is very hard. But there exist different recipes for either injecting magic states or performing non-Clifford gates that we could make work. In particular, there is an upcoming paper by my collaborators and me, where we are showing that there exist dynamic protocols in 2 dimensions that implement non-Clifford gates in basically in 2-dimensional copies of the toric code. But again, to make this work in the setting of this automaton would be a matter of future work. So actually, universal quantum computation is not perfectly clear.
Also, how much does this formalism depend on the square lattice?
So okay, so there are reasons to believe that it shouldn't, but our current construction is not, it's not trivial to generalize it to an arbitrary lattice. So it would be interesting to see how it's done.
Yeah, maybe I have another question. So yeah, in this architecture, actually we still involve measurement, but the algorithm is actually does something like decode the error locally, and you do not need to store the measurement outcome. But the trade-off is that you need a very long circuit.
Yes, in a sense, that's right. Yep.
Okay, and thank you.
Yeah, actually, I have a question. So could you please comment a little bit more on the fault tolerance part? What if your gadgets have some errors? And do you have anything like a threshold, something like that?
Yeah, that's right. Yeah, so we show that we show rigorously that it has a threshold analytically, but the estimate would be very poor. And we also have like some preliminary numerics that show that the threshold is not so horrible. But the idea behind showing that this is fault tolerant is by first we construct the big circuit by self-similarly like concatenating this small circuits such that, we went this direction to create a big circuit, right? But then we actually run a circuit and it's a noisy circuit. So now there exists some noise realization in space-time that we need to consider. And with this noisy circuit, then we ask a question, what is a noisy circuit actually simulating? And then you can compute that. You can sort of find that. So you find that the circuit, for example, with an error that can, for example, fail this entire block, is simulating a circuit that we wanted it to simulate, except what was this gate is simulated inside of that square. So this gate will fail. So that's what it is simulating. So it is simulating a circuit that we wanted it to simulate, except like some part will fail, if that's a small enough part. And so basically in this sense, we had like some error that was confined to this rectangle, and the size of this error was renormalized. So you're kind of finding this renormalization of the error size. And finally, you're asking, what is this circuit, like a simulated circuit, is simulating? And that circuit actually with just a single error that does not corrupt this circuit. So that circuit would be simulating what you wanted. And that's how you show that the probability of you not simulating what you wanted once you go all the levels up is actually exponentially small.
Okay.
And that's how you show fault tolerance. Yeah.
Yeah. Thank you. Yeah.
I have one more question. In the outlook part, you mentioned the direction to generalize this to other like nonlinear or even hard codes. So it seems in this talk, you got some inspiration of how to do this to toric code from the Eisen model. Suppose I want to do it just to some other topological orders, abelian or nonlinear. Do I have to start with some other one-dimensional classical symmetry breaking orders?
So yeah, so I can only speculate because I don't know yet how to solve this problem for other orders. And that's a great question. But for non-abelian orders, I think you don't need a different recipe. And the reason is because, like, just conceptually, you just want to match point like excitations. It's just the operations that have to be different now. but the problem that you're solving is very similar. So you really just need to figure out how to do it operationally, but conceptually it's the same problem. When it comes to other like non-topological orders, like Haas code, that's where things become interesting, because I think indeed you would need to revisit. So Haas code can be, for example, related to some classical fractal codes. And you might need to first consider how to locally correct those and to then learn how to correct Haas code. But maybe there exists a simpler way to do that. So it would be really cool to know.
Thanks.
So inspired by Liu Jun's question, so some quantum code is a product of a classical code, like toric code is a product of two classical icing. So does it imply that once we can know how do we do this serial automata for a classical code, this automatically can give you some contraction for the higher dimensional quantum code?
So that's an amazing question, actually, because so it's a very hard to answer one too, because so I would say that naively the answer is no, but it doesn't mean that you can't make it work in principle. And the reason why naively the answer is no is because when you take a product of two classical codes, in each sector of the resulting CSS code, say X sector, you will have participation of the primal of one of the classical codes and the dual of the other classical code. And for the Z sector, you will have participation of the dual of the first classical code and the primary of the second classical code. So in both quantum X and Z sectors, you will have you will see emergence of both primary and dual classical codes that you're taking product of. So then, why did it work out so nicely for the toric code? Is because both Ising model and the dual to the Ising model is also Ising model, and we know how to correct both. But if you take basically any other code and you know how to correct that code, it's not guaranteed that you will know how to correct the dual to that code, right? So you would need probably. And that's besides that, we also don't quite know how to express this in the language of product of codes, how to describe these constructions. So it would be very, very beautiful to be able to do that, but we don't even first of all have a description in the language of products of codes and the relation between decoding of classical codes and quantum codes. So first of all, we would need such a formalism. And then if we had a formalism, you would definitely need to be able to correct both the primal and dual of the code.
Okay, thank you so much.
Yeah, thank you.
Okay, any other questions? Okay, if not, let's thank Margarita again. Thank you, Margarita.
Thank you. Thank you very much.
Yeah, so now we can all leave. See you.
Yeah, thank you.
Record.